physical properties of the alkanes then. So remember, all alkanes are hydrocarbons, and carbon and hydrogen have similar electronegativities, which means that all of the bonds in here are going to be non-polar. Just get my pen on, there we go. Okay, so because all the bonds are non-polar, this means that all alkane molecules will also be non-polar. And remember, they fall in the non-metal area of the periodic table, which means that they're all going to be simple molecular. And that means that if the bonds aren't polar and they're simple molecular in that non-metal area, that means that they're going to have only van der Waals forces of attraction between molecules. And of course, these are very, very weak. Okay. And there's a graph that actually shows you that on the next page. Let me just, or a little bit further down, sorry, let's just skip to that and fill this bit in first, because this bit makes a little bit more sense here. You can see that as the number of carbons increases, the boiling point also increases. And that comes down to the fact that when the length of the carbon chain increases, the boiling point of the alkane also increases. And that's because with van der Waals, remember, there are more electrons in the structure, which means that the van der Waals forces of attraction between molecules become stronger. And because they're stronger, that means that more energy is required to overcome. Okay, and you can see the trend here, look. So there's the trend. As the number of carbons increases, the boiling point also increases. The first four are actually gases, and then from 5 onwards, they're liquids. And again, you know, as they get longer and longer and longer, eventually they become solids, which is kind of like candle wax, that kind of stuff there. Let me just talk about the solubility with these. Now, for something to be soluble in something else, the intermolecular forces have to be either the same or very, very similar. And what we have in water molecules, remember, is hydrogen bonding, which is very strong. And basically what you would have to do for any alkane to dissolve in water is break the hydrogen bond, which means that the force of attraction that is formed between the alkane and water has to be at least as strong as the hydrogen bonds in water, which of course it isn't, because with the alkane it can only do van der Waals force of attraction. So just giving that in its absolute simplest form, if they're not the same, they don't dissolve, okay? So the hydrogen bonds are much stronger than the van der Waals forces of attraction that we find in alkanes, and therefore they are not soluble in water, Okay, let's move on. So let's have a look at the effect of branching. Each of these are isomers of pentane, so they all have the molecular formula C5H12, but you can see here we've taken a methyl off the end of the molecule and put it here, so it's got a little bit of branching. And then in the on this one here, we've still got that one, but then we've taken another one off the other end and moved that one in as well. And what that means is that this actually affects the boiling point. And I think you can see, look, that as branching increases, the boiling point actually decreases, okay? So as branching increases, the boiling point of the alkane decreases. And if I just draw a kind of circle around these, it'll give you an idea of why. So if I draw a circle around that molecule there, I'll draw a circle around this molecule here and this molecule here, and then I'll change colour with my pens in a minute. Okay, so I think you can see here there's a very large area of contact with that one between the two molecules, which means van der Waals will be strongest there. Here, the kind of contact between the two molecules is slightly less, which means the van der Waals is weaker, so less energy is required, so the boiling point goes down. And this one has the absolute minimum amount here. So I think at GCSE you'd probably called it surface area, but at A-level we prefer to call it points of contact. So this has the most point of contacts, and this has the fewer points of contact here. So let's just fill this last section in here. So the explanation then why the boiling point decreases as branching increases is because there are fewer points of contact between the molecules, which means that the van der Waals forces of attraction between molecules becomes weaker and therefore require less energy to overcome. Okay, and then the final section really here is just to talk through this. When you've done what done here is we have a flask with a side arm, and then we have a thermometer in here, and what we do is we gradually increase the temperature, and then the liquid with the lowest boiling point evaporates first and then kind of condenses down here, and we collect it at this point here. But what we do with fractional distillation with crude oil, what we have is a temperature gradient. So the crude oil that comes in at this point here is heated to its absolute maximum, and then as a gas we allow it to move up the column where it gets cooler, and then when it reaches its kind of boiling point it condenses as a liquid. So these ones in here will condense between about 300 and 370. These ones in here will condense between 200 and 300. These ones here between about 150 and 200, and then what's left here either condenses in this region here, or any of the lighter gases like the first four, they just carry on and we collect those off at the top. Okay, now each of these, because it has such a large boiling range, we call them fractions, because it's not one liquid. One liquid has a boiling point. If you think of water, water has a boiling point at 100 degrees C. Now, all the liquids in here, in this region here, will start to boil at 300 and continue boiling all the way up to 370, which tells you you've got a mixture of liquids of similar boiling points between 300 and 370. So, like when we do fractional distillation of crude oil, what we're doing is we're taking a fraction of the crude oil with similar boiling points. Okay, all of this is described down here, but I just thought I'd take a minute just to explain how it all works, and then we'll pick this up next week.